Right. Hello again, grade 12s. This is part 2 of the reverse chain rule video. So now we're just going to speed it up slightly. After all of the explanation of the first video, we're just going to do some examples and we're going to do different variations, and hopefully you guys should understand this. Okay, so this is example 2 on page 80 of the textbook. Now this one, it doesn't at first seem like an obvious choice for the reverse chain rule, because up until now the reverse chain rule had a compound function, and then next to it had another function that was being multiplied by that compound function. So you should perhaps notice that this one does not have that multiplication over there. But if I just go and I look at this compound function, then my inside function is 3x minus 4. Now the derivative of 3x minus 4 is a constant. Now the moment it's a constant, it means we can manipulate, and that's the whole idea with those constant multiples that I spoke to you guys about in the previous video. So that means even though there's nothing next to it, I can actually go and create that derivative of that inside function, meaning the derivative of the inside function is then 3. So now what I have is I actually have a reverse chain rule situation where I have a compound function over here, and then the derivative of the inside function is then 3, so that is the derivative of the inside function. But again, I am allowed to do this because it's a constant multiple. So always allowed if it's a constant multiple, not if it's a variable. However, because I've multiplied by 3, I have to multiply by a third over here just to make sure that I don't change the sum. It's still got to be the same sum that I originally had. So the third comes down, and then hopefully by now you should understand this whole technique of the reverse chain rule a little bit better. What stands next to it, so what was created by the chain rule, that little bit of a mess, goes back into the Russian doll, it disappears. This, I don't do anything to that inside function, it just stays 3x minus 4. So the only actual integration that I do is I add 1 to that to the power of 5, so it becomes to the power of 6 over 6 plus c. And I can just clean it up by multiplying the coefficients, meaning it's 3x minus 4 to the power of 6 over 3 times 6, which is 18 plus c. And that is something very simple and straightforward, where if you have a compound function but nothing's been multiplied by the compound function, as long as the derivative of the inside function is a constant, you can treat it as though you would any type of reverse chain rule sum. So we're going to do a couple more examples, or actually just I think one more example on this. Okay. So there's another example on this one. So this one again, I'm just going to rewrite it slightly, saying it's 5x minus 2 to the power of a half dx. Oh, by the way, I did mention this in last term's videos. Please don't forget to write that dx, otherwise you're going to get penalized for your notation. You have to always remember, when you write an integral, it's got to show the integral sign and the dx with a function in the middle. Okay, so in this particular one, again, it doesn't at first glance look like a reverse chain rule, but I do see that there is in fact an inside function and a compound function. So if the derivative of the inside function, in this case 5x minus 2, is a constant, which it is, in this case the derivative of the inside function is 5, I can write that derivative over there. Why? Because it's a constant. Only if it's a constant multiple, not if it is a variable. So not if this is, derivative is going to be an x. I'm not allowed to do that, only if it's a constant. And then obviously, because I've multiplied by 5 there, I'm going to multiply the outside by 1 over 5, just so I don't change the actual sum. So I can then set it up as though it is a reverse chain rule sum. 1 over 5 comes down. That little bit of a mess goes back into the Russian doll, so it pretty much disappears. I don't do anything to the inside function, that stays 5x minus 2, but I do find the integral of the outside function. So I add 1 to that, which makes it 3 over 2, and then I divide by that brand new exponent, so I divide by 3 over 2 plus c. And then again, I'm just going to go and tidy up the coefficients. So that's 1 over 5 divided by 3 over 2, so it's 1 over 5 times 2 over 3, which is then going to be 2 over 15. Times that 5x minus 2 to the power of 3 over 2 plus c. Okay, so pretty simple and straightforward. By the way, later on we're going to do a little bit of a shortcut with these ones, but I always find that it's a good idea to discuss them under reverse chain rule before you apply the shortcut. Otherwise, a lot of people just stare at me and go, how did you do that? So just remember this whole idea of the reverse chain rule if my derivative of the inside function is just a constant multiple. Now I want to quickly just talk to you about something called U substitution. Now U substitution is a technique they love teaching at university. So you will definitely, if you go to university and you do mathematics at university level, they will teach you U substitution. In fact, most universities, they don't even refer to the reverse chain rule. They just do all of the reverse chain rule by means of U substitution. Now, nobody will ever force you to use U substitution. So they won't go and say, do the following sum or integrate the following by means of U substitution. But I do find some people kind of like U substitution. Me personally, I don't like it. I never use it. I think it's way too long. I think it's a waste of time. But I do want to show it to you guys just so that if you go to university next year and you do mathematics, you won't go and say, hey, we never learned this in AP Maths. Okay, so hopefully you'll see that we are going to apply exactly the same technique as we do for reverse chain rule here. Good. So, first things first, you need to notice that reverse chain rule will work. So I'm quickly just going to rewrite this, saying it's 2x times x squared minus 4 to the power of a half dx. So again, I've got my little compound function over there, and the derivative of the inside function is going to be 2x. So if you think about it, you could actually just immediately go and you could find your integral using the technique that we've just done. I will go and do it just now, but we are pretty much looking at U substitution at the moment. So let's first look at the U substitution technique. So U substitution says you set U equal to that inside function. So you still need to be able to identify the inside function, which is the x squared minus 4. After you've set U equal to the inside function, you find the derivative of the inside function, which should also make sense because remember, every single time we used reverse chain rule, we did find the derivative of the inside function to go and check whether that little mess lying around next to it is in fact the inside function's derivative. So if I find the derivative of the inside function, I get 2x. Okay. Now, something slightly strange that they do is they say that that means du is then equal to 2x times dx. And you are perfectly allowed to do that because dx represents the difference in x. So you are allowed to multiply both sides by the difference of x, and then you get du is equal to 2x times dx. Now what you're going to do now is you're going to go back to this part of the sum. And you are going to go and you're going to substitute everything that is there, but you're going to substitute it with u. So this integral is in terms of x. You'll see your function is written in terms of x, and it's being integrated in terms of x. But what we are now going to do is we're going to go and we're going to rewrite everything so that it will then become an integral in terms of u. And that is pretty easy to see. 2x times dx, this part right there, can be substituted with du. And then this part right there, that inside part, x squared minus 4, can be substituted with u. So I can rewrite this entire integral and say it is then u to the power of a half du. Hopefully you guys can see that. This got substituted by u, and that 2x dx got substituted by du. Okay, so this right there actually becomes an incredibly easy integral to do. It's an integral where all you have to do is you then have to go and say it's u, take that exponent, make it 1 more, so to the power of 3 over 2, divided by the power of 3 over 2 plus c. And then, please remember, if you do choose to use u substitution, you need to go and substitute u back with x. So if I substitute it back with x, and I just clean this up, meaning if I divide by 3 over 2, it becomes 2 over 3. And then, like I said, u is equal to x squared minus 4. Then you're done. But I think this is a complete waste of time in all honesty. Because if you think about it, if you had used the reverse chain rule, what would you have done? Using the reverse chain rule, you would have checked and said, okay, the derivative of the inside function is 2x, so that works. The 2x is going to disappear. The x squared minus 4 is going to stay exactly the same, and the only thing that I'm going to integrate is that to the power of a half. So it's going to become to the power of a half plus 1, which is 3 over 2 divided by 3 over 2. So you could actually have skipped straight from there to there without going through all of this. So in all honesty, I think u substitution is the exact same thing as chain rule. It's just writing everything down in a very, very cumbersome way. So I do not recommend using the U substitution as opposed to the reverse chain rule, because the reverse chain rule, if you think about it, uses exactly the same technique. The only difference is you don't actually have to go and write everything down. And the first prize in an AP Maths exam is always finish. So save time. Think more, write less. And that's why I prefer the chain rule, reverse chain rule, because think more, write less. This is just a lot of writing, doing exactly what you would have done in one step. Okay, so I prefer to use substitution. By the way, I'm not going to use U substitution again because, again, like I explained to you guys, I think it's a bit of a waste of time. Okay, we're going to go back to this particular example, and I'm not going to do this with U substitution. I'm going to do this one with reverse chain rule. So first things first, we're just going to rewrite it slightly. Oh, I can't do this one with reverse chain rule. This is one I have to actually do with U substitution. Sorry about that. See? What happens when you get confused yourself. Okay, right. Let me quickly explain to you why reverse chain rule will not work over here. Now, first things first, let's just do that. There we go. First things first, if you go and you look at the inside function over there. Okay. The inside function of that compound function is x minus 2. And I spoke to you guys when I said the moment you determine what that inside function is, you need to check whether the derivative of the inside function is actually multiplied with the compound function on the outside. But what you should notice is you should notice this. The derivative of x minus 2 is 1. There's not a 1 or a constant value next to it. There's an x there. And I've spoken to you guys about this. If there's a problem with a constant multiple, you can fix it. But if there's a problem with an x, with a variable, you cannot fix it. So a lot of people go and say, oh, but can't you just take the x out and multiply by... No, you can't. X's can never, ever, ever be taken out of the integral. Only constant multiples can be taken out of the integral and multiplied at the beginning. So please, 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 people, do not assume you can ever, ever manipulate this x. So this is why, with this particular example, you cannot use the reverse chain rule, because there's no way x will ever be the derivative of x minus 2. The degree, unfortunately, is the same, if you notice. Okay. So this particular one, we are going to use U substitution, but we are going to do a slightly different U substitution. So with this particular U substitution, first thing we're going to do, we're going to say set U equal to, again, that inside part, x minus 2. Okay. Then I'm going to find the derivative. That's something you always do with U substitution. You find the derivative of U, and that's going to be just equal to 1. And then I'm going to multiply both sides with dx, so that du is then equal to dx. Now, if you want to just go straight in and do the substitution, you'll realize you have a little bit of a problem. This gets substituted by u, so that will all become u. Dx gets substituted by u as well, so this becomes du. The problem, however, comes with the fact that we still have that little x there. So we are going to just have to go and do a little bit of extra work over here. We're going to have to say, but if u is equal to x minus 2, then x is equal to u plus 2. And that is just to make sure that every single one of these gets substituted by u. So that means we're going to say it's the integral of x, which is now going to be u plus 2, times x minus 2, which is u to the power of a half, dx, which I can substitute with du. And the reason this was useful was because I couldn't actually simplify the original algebra over here. But due to the u substitution, I can now actually go and multiply in. I can use my distributive law and I can simplify this. So I can simplify this to say it's going to be the integral of u times u to the power of a half, which is u to the power of 3 over 2, plus 2u to the power of half du. And that I can now go and integrate. So with this one, I can now go and say u to the power of 3 over 2 is going to be u to the power of 5 over 2, because I add 1 to the exponent and I divide by the new exponent, plus 2u to the power of add 1, so that's going to be 3 over 2, and I divide by that 3 over 2 plus c. And then lastly, this is something a lot of people forget. Please don't forget to substitute the u back, otherwise you're going to lose marks. So we're running a little bit out of space here, sorry about that. So u will need to get substituted by x minus 2. So we have x minus 2 to the power of 5 over 2. And because we're dividing by 5 over 2, we are actually multiplying by 2 over 5. Plus, and then this one's going to be 2 divided by 3 over 2, so it's 2 times 2 over 3, which is going to be 4 over 3, times u, which is that x minus 2 to the power of 3 over 2, plus c. So for this particular one, we were forced to go and use the u substitution. By the way, like I said to you guys, I never ever use u substitution, and even with this particular one, currently I was forced to use the u substitution because I haven't taught you something called integration by parts yet. Later on, we're going to learn that technique called integration by parts, and then with integration by parts, we can even avoid the u substitution here, which you'll see once we do the integration of parts is also shorter than the u substitution. But this is just for interest's sake for now, because we haven't done integration by parts yet. Okay. Right, so let's get back to reverse chain rule, because that's actually what I want you guys to practice. Okay, so with this particular one, and this is from exercise 2.2 on page 82. So we have x times 2x squared minus 5 to the power of a half dx. And again, we have that whole thing. This is my compound function, and we have the inside function. So if I find the derivative of that inside function, I end up with 4x minus 0, so just 4x. Now again, it's not exactly the same, but luckily the only problem is there should be a 4. So the moment it's a constant multiple, I can fix it. So I can put a 4 there so that this becomes the derivative of the inside function, but because I've changed that, I need to change it over here, so that a quarter times 4 is 1. Now again, quarter comes down, 4x disappears, that goes back into the little Russian doll, I don't see it anymore. This stays exactly the same, so that stays 2x squared minus 5. The only thing I have to actually integrate is that to the power of a half. So I add 1, becoming 3 over 2, and then I divide by that new exponent, which is 3 over 2 plus c. And then I just clean up, saying it's a quarter divided by 3 over 2, so it's a quarter times 2 over 3. That's then going to be 3, no. Is it? No. Yeah, it is. Why am I confusing myself now? I am actually confusing myself. A quarter times 2 over 3. 2 goes into 4 twice, so the 3 will stay at the top. Man. I should actually just check it with my calculator. Obviously, too late in the evening for me. This actually is quite... This isn't even a proper AP Maths class because this is pre-recorded. I'm still functioning like normal AP Maths, making mistakes as though it's 7 o'clock on a Friday. Okay, so it's 1 over 4 divided by 3 over 2, just to double check. So that's going to be 1 over 6. I knew I was doing something wrong. Okay. So that's going to be 2x squared minus 5 to the power of 3 over 2 over 6 plus c. So that's going to be cleaning up the coefficients. And maybe in an exam especially, just use your calculator to clean up those coefficients. Okay, some more examples. The next example, number 3, we're again just going to go and prep it. So I'm going to put the x over there, and then I'm going to say x squared plus 9 to the power of negative a half. Careful with that negative a half. And then again, this over there is my compound function. I look at the inside, which is the x squared plus 9, and I say the derivative of that x squared plus 9, that's going to be 2x. Okay, now I agree this is not 2x, but the only issue comes with a constant of 2. And the moment it's a constant multiple, I can fix that, so I can multiply by 2 there, but that means I have to multiply by a half, so half times 2 is equal to 1. So that little outside disappears, the half comes down. The x squared plus 9, I don't do anything to that. The only thing I actually integrate is that to the power of negative a half. So that negative a half, I add 1, which becomes positive a half, and then I divide by that brand new exponent. And then you guys should notice that a half divided by half is 1. So this one will then just be x squared plus 9 to the power of a half, and if you want to, you can just say, but to the power of a half is square root. There you go. So nice and clean, actually. Right, last little example. With this one specifically, we look at that x squared plus 1 and we say, okay, but this is my compound function, this is my inside function. Can that be the derivative of the inside function? Absolutely it can. I can definitely go and I can say that x squared is going to be 2x plus 0. And I agree this is not 2x, but that's really not a problem. Now to fix this one, some of you guys might get a little bit confused with this, but it's really not that complicated. I want to go and I want to make that 2x because it needs to be the derivative of the inside function. But that means I already had a 6 over there. So because I already had a 6 over there, I can then fix it by simply multiplying by 3 on the outside, because 3 times 2x is 6x. So effectively what I've done over here was I've just taken 3 out as that common multiple. So this is now the derivative. That disappears back into the Russian doll. 3 comes down. I don't do anything to that x squared plus 4. Sorry, x squared plus 1. Wow. So that stays x squared plus 1. That one, however, I need to integrate. So that becomes to the power of 4. And then I have to remember to divide by 4 plus c. And then just for interest's sake, because I know I haven't done it for a while, hopefully you guys are trusting me with these ones and you're following along and you're seeing, yeah, I think this works. But just to prove to you, if I find the derivative of this particular one, I'm just going to rewrite it slightly. Then the derivative of that should then be the original sum, because remember it's anti-differentiation when I integrate. So if I find the derivative of that using the chain rule, I go 4 times 3 over 4. The 4 divides by the 4, so I've got 3 left. And then inside is just going to be x squared plus 1, because remember I don't touch the inside initially. That becomes 1 less, so that's to the power of 3. Now according to the chain rule, I then have to find the derivative of the inside. So the derivative of the inside is going to be 2x. Now if I clean all of this up, then 3 times 2x gives me 6x times x squared plus 1 to the power of 3. And then, as you guys can hopefully very clearly see, this is back to the original sum. So I know for a fact that if this is the derivative of that, then the integral is this. So that again is just a nice little check to make sure that you are doing it correctly. Right, so that is pretty much the discussion on the reverse chain rule. We will refer back to it quite often, especially later on when we do a summary of all the different integration techniques. I've uploaded a whole homework worksheet for you guys, just so you guys can practice a bit. It's not that many. I think there's only about 6 sums. There's a memo for it as well. So please go and practice. You have to get a very good handle on this work, because there's quite a few integration techniques. You can't afford not to understand one before you move on to the next one. Thank you very much for listening.